Okay, for the last little bit of class, we're going to dig even deeper than the atomic scale. We're going to dig into the nucleus of atoms and see what's going on there. And there are a couple of important differences that I want to highlight about physics at the nuclear scale compared to physics at the atomic scale. First of all, one of the most obvious differences is the size of things, right? The relevant, what we'll call the relevant length scales. For atomic physics, atoms are roughly the size of the Bohr radius, which we derived to be about half an angstrom. So about 10 to the on the order of 10 to the minus 10 meters, or a little bit bigger. Nuclei, on the other hand, are much, much smaller than that. Nuclei, typical size of a nucleus is about R0, or bigger, right? So R0 is about 1.2 times 10 to the minus 15 meters, right? So that's much smaller than an atom would ever be. And in fact, 10 to the minus 15 meters, 10 to the minus 15th is the metric prefix femto. So this is like a femtometer, 1.2 femtometers, which is much, much smaller than the size of the atom. The atom is mostly really empty space. Now, this number, as I said, is just kind of a typical number. It's sort of the nuclear equivalent of the Bohr radius. Now, the larger the nucleus, the heavier the nucleus, the larger it's going to be. And in fact, a good estimate for the size of a nucleus would be about R0 times A to the 1/3, where A, by the way, is the atomic number of the nucleus. The atomic number of the nucleus is just the total number of protons and neutrons in the nucleus. So, for example, for lithium, which has 3 protons, 3 neutrons, that would have an atomic number of 6. Actually, this shouldn't be 1/2. This should be 1/3. Excuse me. So it's R0 times A to the 1/3, not the 1/2. This is just a byproduct of the fact that if you try to squish a bunch of spheres into a volume, that volume is going to be proportional to 4/3 pi r cubed, right? So if you solve that for r, the radius would then be proportional to the number of spheres that you're packing into the volume to the 1/3, right? So this is actually a pretty good estimate for the size of the nucleus, with RO being 1.2 femtometers. Okay, so the length scales are much, much smaller. Now, since the length scales are so much smaller, think about the uncertainty principle, right? If the minimum length, if the minimum size of the object is really, really tiny, then the minimum speed is actually going to be much, much bigger, because delta r times delta p had better be greater than or equal to h bar over 2 pi, or h over 2 pi. So that means much bigger speeds, which actually corresponds to much greater energies. So things at the nuclear level are at a vastly different energy scale. Whereas atomic transitions tend to be on the order of a couple of electron volts, right? And an electron might go from an n equals 4 to an n equals 2 state and release a photon of a couple of electron volts. But at the nuclear level, the energies are much, much higher. We're talking millions of electron volts, typically mega electron volts. Okay, so the energies are much larger in the nuclear universe. A word about notation. We define Z, capital Z, to be the number of protons in the nucleus. Capital N is the number of neutrons in the nucleus. And capital A is this atomic mass number that I mentioned before, which is just Z plus N, right? And so the notation that we typically use for a nucleus, for example, an oxygen nucleus, oxygen has 8 protons and 8 neutrons, and so its Z is 8, and its atomic mass would be 16. And so it's got 8 protons, 8 neutrons, and so this is the way we typically notate an oxygen nucleus. You can have different types of the same nucleus, right? So we call isotopes of a given nucleus, they would have the same number of protons as one another, but they may have a different number of neutrons. For example, one of the most common examples is the carbon series of isotopes. For example, carbon has 6 protons because that's why it's carbon, and typically it has exactly the same number of neutrons. 6 neutrons would give us carbon-12, right? If you take a lump of carbon out of the ground, you're going to find that most of the carbon is carbon-12. In fact, its abundance in nature is about 98.89%. Right? Most of the carbon that you'll find is going to be carbon-12. However, there are other types of carbon. There's carbon-13. Still has six protons because that's what makes it carbon, but it has 7 neutrons. This is a much less common isotope. In fact, most of it's only about 1 and a little bit % of the carbon that you would find is going to be carbon-13. Which, if you add these two numbers up, you basically get 100%. But there is another isotope that you find, carbon-14, which has 6 protons and 8 neutrons, which is not very abundant at all. In fact, its abundance is about 1.2 times 10 to the minus 12 times the abundance of carbon 12. Right? So it's very rare compared to carbon 12. But of course, if you have a lump of carbon, there will be some carbon-14 in there. And carbon-14, it turns out, is a very interesting isotope of carbon because it's radioactive. And so this lends itself to carbon dating, which we'll talk about. Okay. We talk about atomic masses. You guys are probably familiar with this. It's typically measured in atomic mass units. So the symbol for the atomic mass unit is lowercase u, which in kilograms is 1.660540 times 10 to the minus 27 kilograms, right? Very precise. It turns out we know things to high precision in the nuclear world, and we hit better if we're actually going to make sense of the reactions that we're going to talk about. So the atomic mass number, the atomic mass unit, that's what I want to say, is a very common unit for measuring the mass of a nucleus. Now, bear in mind that if, for example, you wanted to know the mass of a carbon nucleus or something along these lines, when you're looking that up in a table, you need to remember that the nuclear mass would be equal to the atomic mass. That would be the number that's typically staring at you from the periodic table, or whatever table you're looking at is this number, the atomic mass. And to get the nuclear mass, you would have to subtract from that the mass of the electrons. Because the atomic mass includes all of the electrons, and so if you just want the nuclear mass, you have to subtract the mass of the electrons. That's actually an important thing to remember when you're dealing with nuclear reactions. We'll see an example of that in a bit. And then, so this is a very common unit for atomic mass. There's actually a very common unit for atomic energy as well. And it's related to the fact that energy and mass are equivalent. They are equivalent through Einstein's famous equation, mc squared. If we have an object that has a certain mass m, then there's a certain amount of energy associated with that mass, and it's equal to mc squared, right? Since energies are often measured in mega electron volts, if you look at the units, so on the left-hand side we typically think of mass in like kilograms, but if you look on the right-hand side of this equation, it suggests a new unit for mass, right? Especially for the atomic world. If you think of the units with what's on the right here, we would see MeV up on top, because I said that's a typical energy for nuclei, divided by c squared, right? So MeV divided by c squared is actually a unit for mass. And one atomic mass unit, I'll let you verify this on your own, but you can work out that one atomic mass unit is exactly 931.5 MeV divided by c squared. So this is actually a very useful number, right? If you want to convert something in atomic mass units, to this new unit of mass, you'll use that number a lot. Okay? Nuclei have protons that are packed together in a very tight little volume. So, if you put two protons really close together, they're going to feel an enormous repulsive force from the electrostatic force, because it's two like charges that are really, really close together. So in order to get even two protons to hang out very close together at radii on the order of 10 to the minus 15 meters, 10 to the minus 15 meters, there must be another force that's able to resist that enormous repulsive electric force between those two things. And there is such a force, we call it the strong nuclear force. And some general properties about the strong nuclear force. Number one, it is attractive between protons and protons. It is attractive between neutrons and neutrons, and also protons and neutrons. And the nice thing about that is that neutrons don't experience a repulsive electrostatic force. And so they can turn out to act as sort of a glue using this strong nuclear force. Number two, it's very short range. Once you get two particles, two protons, for example, outside of the, say, 1 to 2 femtometer range, the strong force basically disappears, and the electrostatic repulsion will kick in and they'll fly apart. Right? But once you get them inside that magic window of about 1 to 2 femtometers, the strong nuclear force kicks in and they get sucked together. They get very tightly bound. The strong nuclear force does not act on electrons, which means it has no effect on the chemistry of atoms. It only affects the protons and neutrons. And finally, a word about stability. As the nuclei get larger and larger, that is, the number of protons gets bigger and bigger as Z increases, we typically need extra neutrons to help the nucleus from decaying, right? So since the neutrons actually contribute to the strong nuclear binding, and they don't contribute to the electrostatic repulsion, typically as Z gets bigger and bigger, you need more of them to help keep the nucleus happy and in one piece. So for example, as an example, a typical gold nucleus, Au, gold, has an atomic number of 79, so 79 protons, but an atomic mass number of 197. So the number of neutrons is actually 118 compared to only 79 protons. Right? So in gold, those extra neutrons are essentially serving as strong nuclear glue that helps keep the whole atom together and stable. If you were to take away some of those neutrons and maybe make 79 195 gold, then there's going to be a little bit too much repulsive force, and it's actually going to become an unstable isotope of gold. If you were to make a plot of the number of neutrons as a function of the number of protons, right? If you just do the n equals z line like that, so this is the line n equals z, most of the elements live on this side of the wedge, right? In fact, if you sort of look at a plot of what happens on the periodic table, as z increases, you typically need more than the same number of neutrons to keep the whole thing stable. So this is the type of relationship that you see. So what happens to these unstable nuclei? Well, it turns out that they, if I do make something like gold 195, it's going to be unstable. It's going to be too close to the diagonal here, and it's going to break apart. It's going to become radioactive. And that's what I'm going to talk about next. Okay, so when a nucleus has either too many or too few neutrons for stability, it becomes radioactive, which means that it may spontaneously, at some point in time, it's hard to predict when, in fact impossible to predict when, it will spontaneously emit a particle, something. And typically what it emits comes in one of three types. And the three types of radioactivity were discovered long before we actually even knew what the radioactive particles were that were being emitted. They were called alpha, beta, and gamma, just as a bookkeeping, as a way of keeping it. Now, of course, we know in more detail what an alpha particle is, what a beta particle is. And so let's talk about the first type. There's alpha decay, which is really just the spontaneous emission of an alpha particle. And an alpha particle is, as you guys know, 2 protons, 2 neutrons, which is essentially just a helium nucleus, right? So a helium nucleus has two protons, 2 neutrons, and so that would be the symbol for the helium nucleus and an alpha particle. Now, when the alpha particle comes out of the nucleus, it obviously doesn't have any electrons, so it's not really a helium atom, it's just a helium nucleus. But of course, once emitted, the helium nucleus can then grab electrons from anywhere and become a helium atom. But when it comes out of the nucleus, it's just the helium nucleus, right? So an example of a particle, or of an atom that does undergo alpha decay is an americium nucleus. Americium has 95 protons, and its atomic number is 243. And this is unstable, and so we call it the unstable parent nucleus. And so it emits an alpha particle. And what you're left with, the nucleus that you're left with after this, must obey some certain rules, right? I mean, for one thing, we need to keep the total atomic number on both sides of the reaction conserved. So 4 from 243 is 239. So whatever element it is had better have an atomic mass number of that. And also the z's have to add up on both sides to the same number, so it better be 93. If you look up on a periodic table what has 93 neutrons, or excuse me, 93 protons, you'll find that it's neptunium. And so these are the daughter nuclei. And they may be stable or unstable. Neptunium-239 is a stable isotope, but it may not be, in which case, excuse me, in which case the daughter nucleus might then continue to decay into various other things. Okay, so in this reaction, since it's spontaneous, energy is going to be released. And so the question is, how much energy is released? So how much energy is released in this reaction? To answer that, you really need to look at the masses of the particles on both sides of the reaction. For example, on the left-hand side of the reaction, what I'll call the initial mass, if you look up the atomic mass of americium-243, you can look that up online or in a table, wherever, you find that it is 243, and I'm going to keep a lot of significant digits here for reasons that you'll see. So it's 243.061374, and that's atomic mass units. That's what you typically find when you look in a table like that, is something in atomic mass units. Now the final mass would just be the mass of the alpha particle, or in this case, if you're looking it up in a table, you're going to actually get the mass of a helium atom, which is okay because there's the same number of electrons on the right-hand side as there are on the left-hand side, so we can include the mass of an electron, it won't really matter, or mass of the electrons, and it won't matter. And so in the final picture, if you look this up, you find that the mass of helium-4 is 4.002603 atomic mass units. And the atomic mass of neptunium is 239.052932 atomic mass units, right? So I'm keeping a lot of significant digits here. If you add these two numbers up, you get 243.055535, which, if you notice, is actually a little bit smaller than the initial mass, right? So the final mass is a little bit smaller than the initial mass. So in fact, if you were to calculate the change in the mass over the course of this reaction, you find that it's negative 0.005839 atomic mass units. Now I hope you see why we kept all of those significant digits when we were doing this. So we have actually lost mass in this reaction. And so where did the mass go? Well, according to Einstein, it must have gone somewhere, and it went into kinetic energy of the daughter particles, right? So after this happens, you get a helium atom, a helium nucleus with a lot of kinetic energy, and a Neptunian nucleus with a little bit, kind of like, again, a bullet fired from a gun. So how much energy is released? Well, we can use Einstein's equation, which tells us that the energy release is just going to be proportional to mc squared. I use absolute values here because, in this case, delta m is actually negative, so this energy is released. If delta m had wound up being positive, then energy would have been required. It would have required energy for this reaction to take place. And so, when I'm actually calculating this at the end, I've got 0.005839 atomic mass units. And if I convert that using my new conversion factor, 935.1 MeV divided by c squared per atomic mass, and then multiply that by c squared here, you can see that these c squareds cancel, the u's cancel, and I wind up with something in mega electron volts, and that number winds up being 5.439 electron volts. And so that's the answer. So that's how much energy was released in this reaction. Another thing that can happen would be the second type of decay, beta decay. Now, a beta particle is just either an electron, which we would write as a beta minus particle, or a positron, which is a particle that has exactly the same mass as an electron, but a positive charge. Exactly the same magnitude charge too, but positive. Now, why don't we just call them electrons and positrons? Well, because we want to distinguish these electrons from the ones that are actually orbiting the nucleus, right? Which are the chemical electrons associated with the element. These are actually coming from the nucleus, so we give them a different name. But once they're emitted, they just become ordinary electrons or positrons. So beta decay. I'll give you an example of a reaction. Carbon-14, which I mentioned before was radioactive, decaying into nitrogen, which has 7 protons and 14 neutrons, right? Plus a beta minus particle. Now, in our notation of Z and A, you can think of an electron as just having a Z of -1 and an A of 0. And you can see that, again, the A's add up on both sides, as do the Z's, right? Now, this turns out to be a pretty important decay process. And if you actually do the same process where you calculate your delta M's and you plug it into E equals delta M C squared, you find that the energy released in this reaction ought to be 0.156 MeV. You can try that on your own if you're interested. So you would expect, since the electrons are so much less massive than the nitrogen nuclei, you would expect that these electrons would come off with a very well-defined energy, this. But it turns out something interesting happens. If you were to actually plot, if you have a carbon-14 sample and you were to plot the number of electrons that come out with a specific energy, as a function of energy, again, you would expect the graph to be very sharply peaked right here at 0.156 MeV. You would expect virtually all the electrons to come out with this energy, but that, in fact, is not at all what you find. You find a plot that looks something like this. Right? So this is what you would expect, and this is what experiment shows. So this was actually a very surprising result, that we didn't have these monoenergetic electrons coming out of carbon-14, and instead you found this spread. And the only way it could be described, and it was proposed by Wolfgang Pauli in 1930, the only way this can be described is that this reaction is not quite complete. In fact, there must be another particle here on the right-hand side of the equation that's carrying away some of the energy, which means that the electrons would actually come out of the reaction with less energy than what we predict. But it must be neutral, it must not have any charge, and it must be very low mass as well. You can think of it as a little neutral particle, or a neutrino. That's exactly what belongs on the right-hand side of this equation. Because this was an electron that was emitted, a beta minus particle, we call it an electron neutrino. And it turns out another thing, if an electron is emitted, if a beta minus particle is emitted from a reaction like this, it turns out that you get what we call a new bar, a neutrino with a bar over it, which means actually an anti-electron neutrino. Anti-electron neutrino rather than just an electron neutrino. If this had been a beta plus particle, then we would just get a regular electron neutrino. Now the reasons for that and what an electron versus an anti-electron neutrino are is the domain of particle physics, which is a little beyond what we're going to talk about here. In fact, neutrinos turn out to be pretty interesting things, and there's a lot of interesting work going on in the study of neutrinos. In fact, not that long ago, I think in the 80s or the 90s, it was discovered that neutrinos can do very funny things. They can sort of transform from one type of neutrino to another. That's called a neutrino oscillation. And it turns out that these little things are super hard to detect. In fact, one of the largest neutrino detectors in the world is the Super Kamiokande experiment in Japan, and it involves this enormous underground tank of water. And essentially, there's tons and tons, countless numbers of neutrinos bombarding us every second from the sun, but only, they may only detect one event every day with this enormous detector because neutrinos really don't like to interact with matter that much. So it's really hard to detect these guys. All right, so in class we'll do a couple more reactions with beta decay just to get some practice with this. Okay, the third type of radioactive decay that can happen is gamma decay, and that involves the release of a gamma ray photon. So it's not exactly the same type of radioactivity that we've been talking about before. The other two types of radioactivity, you have particles coming out that have mass. For gamma decay, you have a photon coming out with no mass. So as an example, in the reaction that we just talked about, the carbon-14 decay into nitrogen-14, what you get as a result is nitrogen-14, but the nitrogen is in an excited state. Now, I don't mean that the nitrogen, the atoms are at a higher energy level. I actually mean that the nucleus itself is in an excited state, right? And so I put a star here to indicate that the nitrogen is in an excited state. And through the process of gamma decay, it decays to the ground state. So it's still nitrogen-14. It doesn't change the element at all. But we get a photon in the process, right? And so this is now a stable nitrogen nucleus. So in much the same way that an atom, like a hydrogen atom with an electron in an excited state, it may decay to the ground state and in that process emit a photon of a few eV, right? This photon, on the other hand, because we're talking about a nuclear excited state, it decays. This photon actually has a lot more energy, so this is typically on the order of MeV, so a very high energy photon, a gamma ray photon, right? But this is a simple process that also happens commonly for these radioactive elements, and it always happens because the nucleus is in an excited state and decays to a ground state. All right, so these are the three types of radioactivity that are most common, and we'll do some more examples in class.